Okay, Friday we kind of discovered things with an example that we wondered, well, is it always true? Is it always true that the identity from one group is mapped to the identity of another group if the groups are isomorphic? That the inverse, or that if x goes to y, the inverse of x goes to the inverse of y, are inverses matched under an isomorphism. And so those are actually problems in the book, B1 and B2, but I do want to look at those two and probably another one or two just on the idea of if we have an isomorphism between two groups, what does that tell us? And can we prove it? So here's some things that we've got. If G1 and G2 are isomorphic groups, with isomorphism F, then F of E1 equals E2, where E1 is the identity, the book calls it the neutral here, but the identity in G1, and E2 is the identity in G2. So that the identity is mapped to the identity if we have an isomorphism. And they do actually give us a hint here. They say, hint, in any group there's exactly one neutral element, show that F of E1 is the neutral element of G2. So based on the hint, what we need to show, F of E1 is the identity in G2. That's what the hint indicates is going to be the best way to handle this, that F of E1 is the identity in G2, because there's only one identity. So if F of E1 acts like the identity, it is.
So is that where in that third line where it says where E is identity in G1, and does that say E2?
Yeah, I should put E2 over here. E2 is the identity in G2. So we've got two groups, they each have an identity. And so the question is, if it's an isomorphism, does the identity of the first have to map to the identity of the second? And this theorem is saying, yes, they have to. That's what has to happen if we've got an identity, or if we have an isomorphism. Which then in terms of, let's say, our second question that we haven't really talked much about yet, if we've got two groups and we're wanting to know if they're isomorphic, what kind of mapping should we do? Well, one of the things the mapping will have to do is send the identity to the identity, because if it doesn't, there'd be no way it could be an isomorphism. So at least it kind of helps us begin to think about where we could send things. Because if it is going to be an isomorphism, the identity has to go to the identity. So this is what we're going to need to show. Well, how do we do that? How do we show something's an identity? So as we think about this, what do we need to show to show that an element's the identity? What's the identity do? Doesn't change anything. So show that, say, B F of E1 equals F of E1 B for all B in G2. If we can do that, then that element F of E1 is the identity, because it acts like the identity. That's how the identity acts. It doesn't change any other element in the group. And one of the things we've got to watch as we do this, which group are we in? So we're trying to show that this F of E1, which is an element in G2, is the identity for G2. So we've got to be pairing it with things in G2. Now, we don't know what the two groups are. We don't know what the isomorphism looks like. So there's one other thing we kind of have to think about then as we work with this. I mean, this is what we want to show. Is there anything else we would know as we look at this, say, about every element B in G2?
Shouldn't every element in BG2 have an element in a G1 element corresponding to it?
Because
They're all mapped to each other.
they're all it's an on-to mapping. That's exactly the key we need. So for each B in G2, there is an A in G1, so that F of A equals B, since F was on 2. Every output comes from somewhere. Okay. Well, now let's see if we can begin to piece some things together. This is what I need to show. So let's just consider some B in G2. And we need to look at, well, what is B F of E1? We hope it's F of E1 times B. I mean, that's where we're going. We just have quite a bit of ways to get there. But based on what we learned here, B F of E1 is F of A, F of E1 for some A in G1. And actually, I've forgotten one thing. Not only do we want to show this, we want to show this is equal to B. Okay. So at least now we've got F of A times F of E1. Anybody see anything we can do with that?
F of E1 is equal to E2.
F of which say?
Read second line, left side.
Okay, so second line.
No, left side of the board.
Oh, all right, over here. Oh, yeah, I mean, we don't know that F of E1 equals E2. That's what we're trying to prove.
Got it.
So we used one fact about an isomorphism to come up with this A. Are there other things we know about an isomorphism that might help us do something here? It's actually kind of on the screen here as well. If we've got an isomorphism that preserves the operation. So we can either map things first and then combine, or we could combine first and then map. Since F is an isomorphism, either order of doing that operation is the same. Do we know anything else now? Do we know what A times E1 is? It's A. E1 is, and it is the invert, or the identity, in G1. And f of a was b. So I haven't gotten to this part yet, but I jumped straight to b times f of e1 really is equal to b. Guess we could also jump from here, since it's the identity. The identity does commute with every other element. We don't know about everything else, but at least the identity commutes with everything else, because it always gives the original element. So again, since E1 is the identity in G1, and this is then, well, what can I do with that? F of the product. Kind of looking at where I'm heading, I want f of E1. Is there any way I can get f of E1 by itself?
You could separate them.
You can separate them. An isomorphism, you can combine then map, or you can map and then combine. Since f is an isomorphism. And then again, f of a is b. I guess I'll leave that off there. We got the equal b, in the middle. But both of these are equal to b, and that's what we needed. In either order, b times f of e1 is b, so f of e1 is acting like the identity. Well, only one thing in the group acts like the identity, and that's the identity. So if you happen to stumble on something else that's acting like the identity, even if it's got some other name, well, it really doesn't have another name. It is the identity. There's only one of them. So that was the hint here, to show it's the identity, show that it actually acts like the identity. Now, as we were working through this, it was definitely key to kind of get a sense of, how exactly are we going to do this, and what exactly does that mean? And also, for a couple key points, remember, what exactly does the fact that I have an isomorphism tell me? It tells me B is coming from somewhere, and it tells me the operation is preserved. And both of those were very key facts as we put this together. So we're looking at two groups. If they are isomorphic, the identity has to map to the identity. Also then, inverses have to map to inverses. That's kind of the second thing they want us to prove, is that f of A inverse equals f of A inverse. So we need to show that f of A inverse equals f of A inverse. I guess I was a little careful in how I say it. F of A inverse equals f of A inverse. And again, we've got to think, how am I really going to show that? Well, not only is the identity unique, each inverse is unique. So if we can find an element that acts like an inverse, it is. So to show this, what we need to show is, well, we know that f of a inverse satisfies f of a times f of a inverse equals f of a inverse times f of a equals the identity. So we know that's what it does, and so if we can show that f of a inverse actually equals the identity, then this element is acting like the inverse. It must, in fact, be the inverse. So let's do the first part. F of A inverse. We're hoping that's E2. Anybody see anything we can do with that?
Combine them on the inside.
It's an isomorphism, so we could either map first and then combine, or we could combine first and then map. What does that do for us? I mean, we can do it. And that's another thing. I mean, there's a difference between thinking, what can I do, and does it help me? So if you see something you think you can do, try it. Even if you're not sure how it would help you. Try it, see what happens, then step back and say, okay, did that help me? Or what can I do now?
F of 1? Maybe F of 1?
Well, f of E1, yeah.
Oh,
A times its inverse is f of E1. That's what we mean by inverses. An element times its inverse back in G1 gives the identity in G1. Where does the identity in G1 map? We just did that proof. It goes to the identity in G2. The identity maps to identity. Our previous proof. Similarly, if we do the other order, f of A inverse f of A, well, same type thing we did here. We could either map first, which we did here, and then combine, or we could combine first and then map, since F's an isomorphism. And in group G1, A inverse times A is the identity, and f of the identity in G1 is the identity in G2. And so we accomplished what we set out, that this element, f of A inverse, does act like the inverse of f of A. Well, if it acts like it, it is, since there's only one inverse. If we happen to stumble on something that acts like the inverse, well, that's our inverse. Now, we haven't done a lot considering the second question. I said there were three questions. Given specific groups and a specific mapping, is it an isomorphism? Was the first question. The third question was, if we've got two groups that are isomorphic, then something was true. And we can finish up and actually prove something is true. The second question, if we have two groups, are they isomorphic? So let's think a little bit more about that type of question. So suppose G1 is the group, say 0, 1, 2, 3 under addition, or Z4 under addition. And say group G2 is 0, 4, 8, 12 under addition in Z16. So the multiples of 4. Question now would be, well, do we think these groups are isomorphic? Is it merely we kind of rearranged or renamed some elements that they have essentially the same structure all the way through? Well, this question, unfortunately, for us to say yes, we have to come up with F and show it's an isomorphism. Anybody have any ideas what might work for a mapping here?
Multiplication times 4.
Okay, because I mean, yeah, we went from 0, 1, 2, 3 to multiples of 4. Yeah, why don't we try that? So 0 goes to 0, well that's good. If the identity doesn't go to the identity, we could stop right there. It's not going to be an isomorphism. 1 goes to 4, 2 to 8, 3 to 12. It's 1 to 1 and on to. So it's reasonably straightforward to check that it is 1 to 1 and it is on to. If it were more complicated, we'd probably have to do a little bit more work showing that. Final question is then, does it preserve the operation? So if we take, say, A plus B and then map, do we get the same thing as if we map first and then combine? In this case, the combination is also addition in a different sense, but it's still addition. Modulo 16 as opposed to modulo 4. So what's f of A plus B? And our map is f of x is 4x, so if we've got something more complicated, the mapping is still 4 times whatever the input happens to be. Similarly on the other side, f of A is 4 times the input, f of B is 4 times the input. Are those two the same?
Yes.
Yes, that's the distributive property. So they are isomorphic, or F is an isomorphism. So to say two groups are isomorphic, there has to be an isomorphism. So I guess technically we showed F was an isomorphism, and so the original two groups are isomorphic. Let's think of a different group. Trying to think. Last time I gave an example that had 4 elements. We were doing multiplication in Z something. I didn't write down what that example was. Anybody find that in your notes? Actually, I guess this would work. I think if we look in Z8 only at the odd numbers and with the operation multiplication, one is the identity, right? See, 3 times 3 is 1. What's 3 times 5? 7. And 3 times 7? 21, otherwise known as 5. And so 5 times 3 is 7. 5 times 5, is that 1? 5 times 7 is 35. Is it 3? So I think this is commutative. So 3 times 7 is the same as, or 7 times 3 is the same as 3 times 7 was. 7 times 5. What's 7 times 7? 1. All right. So we have these two groups. Do we think these two are isomorphic? Here it's not obvious what a mapping ought to be, or even how we begin to kind of approach this. Turns out in this particular case there's something inherently different in the structure of the two groups. G1 is actually cyclic. We could generate it with an element. 1 plus 1 is 2, plus 1 is 3, plus 1 is 0. It's a cyclic group. G2 is not. 3 times 3 is 1. 5 times 5 is 1. 7 times 7 is 1. We can't start with one element and generate the whole group. So G true is not cyclic. If there's an inherent difference in structure, there's no way the two groups can be isomorphic. The whole idea of isomorphic, in a sense, is the groups are essentially identical. All we've done is change the names of everything. Isomorphic groups, the structure is the same in both groups. So if we happen to come on two groups that are not structured the same, well, they can't be isomorphic. So cyclic and not cyclic. Another way I guess we could have done this is to sort of think of, if there is an isomorphism, f of 1 inverse would have to be f of 1 inverse. But looking wherever 1 goes, everything in this group is its own inverse. In G2, each element is its own inverse. Whereas in G1, that was not the case. What is the inverse of 1? The inverse would be 3. What are we adding to 1 to get the identity? Can f of 3 equal f of 1? If we really have an isomorphism. No, the isomorphism is supposed to be 1 to 1. Each input is supposed to go to something different. So there's no way that we could build an isomorphism here where we've got some elements that aren't their own inverse and we're trying to map to a group where everything is its own inverse. So again, that's kind of a difference in structure. The book, I think, gives some other examples in the section of some places where there'd be some problems with groups not being isomorphic. If one group is commutative and the other one's not, there's no way you could get them isomorphic. Because if elements commute in one group, well, they'd have to commute in the other group, because the operation's preserved. So if they're commuting in one group but not in the other, well, you can't pair things up and preserve the operation. We really haven't talked about groups generated by 2 elements. We've only looked at them generated by 1 element. They just list a few things of where there might be some difference in the structure of the group. A rather amazing result they give is what's known as Cayley's theorem. Every group is isomorphic to a group of permutations. So even though we didn't really look at it this way, and probably don't really want to look at it this way, this group is isomorphic to some group of permutations. Well, since this group is cyclic, it would need to be a cyclic group, so I think if we did, say, 1, 2, 3, 4, so what it generated uh, 1, 2, 3, 4 squared is 1, 3, 2, 4. 1 goes to 3, 3 goes to 1, 2 goes to 4, 4 goes to 2. If we cube this, 1 goes to 4, which goes to 2. No. 4 goes to 3, which goes to 2. And if we do it 4 times, we're back to the identity. If the groups are cyclic, we could send a generator to a generator. Because then the generator squared, well, has to go to the generator squared. It will have to preserve the operation if you send generator to a generator. So any cyclic group of a certain size is isomorphic to all the other cyclic groups of that size. Just pair up the generators. From there on, it defines how everything else would have to be matched up. Let's look at one more kind of very theoretical looking result. So H3 here. Let G be any group. Prove that G is abelian if and only if the function f of x equals x inverse is an isomorphism from G to G. So this one's kind of unusual in that we're treating the group G1 and G2 as the same group. So they're both 0, 1, 2, 3 under addition, or as an example, just to kind of illustrate this with a concrete example. The mapping they propose using here is send x to its inverse. So if that's the case, where would I map 1 to? To its inverse. Where's 2 going to go? To its inverse. 0 is going to go to its inverse, which happens to also be the identity, and the identity has to go to the identity. Where is 3 going to go? To its inverse. So that's kind of a concrete example of this idea here in H3. We've got a group, we're doing the mapping, send every element to its inverse. Is it an isomorphism or not? So we're proving this is an isomorphism if and only if G is abelian. Well, let's look at f a little bit. So f of x is x inverse. Do we think that mapping's onto? Do we get every possible output? If I want to know what maps to A, can anybody think of something that we know would map to any potential output? A inverse. F of A inverse would be the inverse of A inverse, which is A. So it is onto. We do get every possible output. What about 1 to 1? So if f of A happens to equal f of B, then A inverse has to equal B inverse. If we take the inverse of both sides, A has to equal B. So the mapping is onto, it is 1 to 1. Regardless of whether the group happens to be abelian or not. So the question here is, what does abelian have to do with finishing this up? And notice this also says if and if, so if and only if. So there's actually two things going on here that we need to prove. If G is abelian, prove F preserves the operation. And if F preserves the operation, G is abelian. We'll see if we can do, should be able to get one of them done in 6 minutes. Whether we can get both of them done or not, I'm not sure. So let's work with this one. We want to prove that f preserves the operation. So f of AB, we ultimately want that to be f of B. F of A, f of B. That's what we need to show to prove that the operation's been preserved. So f of AB, what's that equal to? What does our mapping do in this particular case? It takes the inverse. So it's the inverse of AB. From previous work, do we happen to remember what the inverse of AB is? It's B inverse A inverse. It is the opposite order.
If it's abelian, isn't it commutative?
That is true. If it's abelian, it's commutative. So any two elements, we can put them in the other order. So this would be A inverse, B inverse, since G is abelian. And A inverse is f of A, B inverse is f of B. So if we are allowed to switch that order, yes, we are going to preserve the operation. And if the group is abelian, yes, the order always switches. We can switch the order. If we didn't know it was abelian, we'd be kind of stuck here. Well, we'd be very much stuck here in trying to get from here to there. Because we'd have f of B times f of A, and then we don't know that that's the same thing. Okay. Well, now we need to prove that G is abelian. So we need to prove that AB equals BA. Well, we know F preserves the operation, so somehow we've got to get F in there.
F of the inverse of AB.
Okay, so you want to say F of AB inverse? Is that right? That'll work. That's what F does. F takes the inverse of any element. And that's kind of what we did over here in terms of onto. How do we know that we get a certain element? Well, it comes from its inverse. So now we've got F in there. F preserves the operation, but right now these two are a single element. So this would be what? F of B inverse A inverse. The inverse of a product is the product of the inverses in the other order. What can I do now? Separate. Why can I separate? It preserves the operation, so we can separate. Since we're assuming here F preserves the operation, if we need to separate, we can. Or if we think separating would be helpful, we can. I mean, at this point, I guess we don't know what we need. We're trying things, hoping for an aha moment. Well, what do we have now? mean, f of B inverse is B inverse inverse, which is B, and f of A inverse is A inverse inverse, which is A. And so, well, AB is going to have to equal BA. If the operation is preserved, AB will have to equal BA. The group will have to be abelian. Now, this particular one looks a little weird because surely a group is isomorphic to itself. Just don't do anything to any of the elements. Map every element to itself. Just use the identity mapping. Yeah, that's going to preserve the operation. The group has the same structure as itself if you don't do anything to any of the elements. But a very abstract concept that I don't think we will ever get to in this course, but in a graduate level abstract algebra or another abstract algebra, you would, is to look at the group of all isomorphisms of a group. All the mappings that are isomorphisms. If you would compose two of those isomorphisms, you're going to get another isomorphism. And so you could have a group constructed out of all the mappings that work as isomorphisms on a group. And that is considerably more abstract than anything we will talk about. But it is helpful sometimes to at least just kind of think, well, can I do any of this? And I'm not sure who began to kind of decide what we could do and couldn't do as we look at groups. But just in terms of that question, if we've got two groups, are they isomorphic? Well, certainly a group's isomorphic to itself. Is there any way other than sort of the natural one? And somebody discovered, well, this would work. Actually, I think, back to our other example, 1, 2, 3, 0, I think if we took f of x to 3x, which I guess actually it's the same as this, 1 goes to 3, which is its inverse, 2 goes to 2, its inverse, 3 goes to 9, its inverse. Just kind of a different way of looking at it, but it's still kind of this mapping with that. So, we've got a couple more topics we'll look at. You've got the homework set that you're working on that's due next Tuesday, so that we can get questions on Monday as well. But we've got a couple days to look a little bit more at cyclic groups. The cyclic groups actually turn out to have a whole lot more structure than we've even mentioned so far. If we can just figure out what generates them, that really helps us describe everything about them. So that's what we'll be looking at the next couple days.